Welcome to Tech Learners. In today's lesson, we will be talking about solving differential equation. And today we will discuss the second method, that is solving homogeneous differential equation. In the previous lecture, we had already seen how to solve equations with the variable separable method. And that method will be used here also. So if you have not watched that video, so I request you to please go and watch that video first and then come back to this video. So let's see how we can solve the homogeneous differential equations. First, let's see what is the type of the homogeneous differential equation. So here the type of equations which is can be written in the form of dy by dx is equal to, in numerator, a function in x comma y, and in denominator a function in x comma y, such that each term of the function f and phi will have the same degree. Let's see with an example. Here you can see this is one homogeneous differential equation. It is written in the form of dy by dx is equal to, in numerator we have some function f in x and y, and in denominator also we have some other function phi in x and y. So in this function, let's say the first term 3xy, the degree of 3xy is 2 because x to the power is 1 and y to the power is 1. So we'll sum up both these. So the degree of 3xy is 2. Similarly, the second term in the function f, the degree is 2 because it's y square. So the degree of this second term is also 2. In denominator, let's see, this is phi of x comma y. The degree of first term, this is 3x square. So the variable x has power 2. So the degree is also 2. Here it is x dot y. So x degree 1, y degree 1. We'll sum up these two degrees and the combined degree of this term is also 2. So we can see in this function, this term has degree 2. This term has degree 2. This term has degree 2 and this term also has degree 2. So such type of equation, differential equation, is known as the homogeneous differential equation. Let's see one more example. Here you can see this is dy by dx. We can write it into the dy by dx form. So each term, so this is term 1 x square degree 2, second term y square degree 2, and this is another term xy, this is also degree 2. Let me write this in the homogeneous form. So we'll combine this dy by dx. So this will be dy by dx is equal to, we'll keep this xy here and we'll bring it x square plus y square here. So this is now homogeneous equation. This is function f x and y, and this is function phi. So this is term xy with degree 2, this is degree 2, and this is degree 2. So such equations are called homogeneous differential equations. Now let's see the working rule, how we can solve these homogeneous equations. So let's come to the working rule. We have to perform two substitutions in this. We'll substitute y as vx. So we have taken another variable. So we'll substitute y as vx, and the other substitution is dy by dx as v plus x dv by dx. So this can be achieved by differentiating this equation. So if you differentiate this equation, so let's differentiate this equation. On the left hand side, this will be dy by dx, and this will perform the product rule. So according to the product rule, first function v, second function x, the derivative of x is 1, plus second function as it is, which is x, and derivative of the first function. So this is dv upon dx. So we have to substitute y as vx and we have to substitute dy by dx as v plus x dv by dx. Just by doing this, our equation will be reduced in two variables, v and x only. So we have eliminated y. And why we have done? We have done this just to convert this equation into variable separable format. So once we do these substitutions, the new equation will be reduced, which will only involve v and x, and we can solve that equation using variable separable method. That's why I have asked you, if you have not watched that variable separable method, so please watch that video first and then come back to this homogeneous differential equation. Let's start with question number 1. This is dy by dx is equal to 3y square plus 2xy divided by 2xy plus x square. Let's check whether this is homogeneous or not. This is first term with degree 2. This is second term degree 2 in function f. In denominator function phi. This is xy degree 2 and this is x square degree 2. So we'll start with step number 1. We'll substitute y as vx and dy by dx as v plus x dv by dx. So let's substitute this. This will be v plus x dv by dx. The substitution on the left hand side. Right hand side, this will be 3 vx square plus twice of x vx divided by twice of x vx plus x square. So let's take this common. X square, this is 3v square x square plus 2v x square. In the denominator, this is 2v x square plus x square. You can see you can take x square common from the numerator and x square common from the denominator, and this will cancel out. So this will remain 3v square plus 2v divided by 2v plus 1. So on the left hand side, this is v plus x dv upon dx. We'll take this v on the right hand side. So this will be x dv upon dx is equal to 3v square plus 2v upon 2v plus 1 minus v. Now we'll solve this by taking the LCM. So this will become 3v square plus 2v minus 2v square and minus v divided by 2v plus 1. So now we'll solve it. 3v square minus 2v square. So we're left with v square. Then 2v minus v. We're left with v only. And this is divided by 2v plus 1. So this is on the right hand side. On the left hand side, we have x dv and dx. Now we'll try to separate the variables. We'll try bring all v's and dv on the left hand side and x dx on the right hand side, as we used to do in the variable separable format. So this will be 2v plus 1 upon v square plus v with dv, and on the right hand side this is 1 upon x with dx. So now we can see that this is a variable separable format. So we can solve this just by integrating on both end the sides. So we just solve this by integrating. So let's solve it. This will be 2v plus 1 v square plus v dv is equal to integral 1 upon x dx. So on the left hand side, we can solve this using the substitution method. So we'll substitute this v square plus v as t. So let's do the substitution. This v square plus v is substituted as t, and then we'll differentiate this. So this will become 2v plus 1 dv is equal to dt. So left hand side, v square is 2v plus 1 is 1. So 2v plus 1 dv is equal to dt. So we can see this 2v plus 1 dv is equal to dt, and v square plus v is equal to t. So this integral will become dt upon t is equal to integral 1 upon x dx. Now integrating, this is log t is equal to log x plus c. Now we can substitute this t back. So this will be log v square plus v is equal to log x plus c. And then we'll substitute this v back. So we had started with the relation y is equal to vx. So v will be y upon x. So we'll substitute this back. So this will be log of y upon x square. So this is y square x square plus y upon x is equal to log x plus c. So this will be our final solution for the given homogeneous differential equation. In this question, we can see this is dy by dx is equal to y upon x plus x sine of y upon x. Let's check the degree of each term. Here we can see y to the power 1. This is x to the power 1. This is x to the power 1. Y to the power 1 and x to the power 1. So the degree is same. So this is a homogeneous differential equation. Then we will simply substitute accordingly. We used to do. We substitute y as vx, and then we substitute dy by dx as v plus x dv by dx. So let's do it. So on substituting, this dy by dx will become v plus x dv upon dx, and on the right hand side we can see this y upon x. So from here y is equal to vx, we have y upon x as v. So this will be y upon x as v plus, then we have this x, and again this y upon x will be substituted as v. Now this is x dv upon dx is equal to, we transfer this v this side, so this v and this v will cancel out, and this will become x dot sine v. So now this equation is in only x and v. Now we need to separate the variables. So let's bring sine v on the left hand side and x dx on the right hand side. So this will be 1 upon sine v dv is equal to 1 upon x dx. So now you can see this is a equation in two variables, v and x only, and this is can be solved using variable separable method. So we will simply integrate this on both the ends. So now integrating on the left hand side, this is integral 1 upon n sine v dv. This is equal to integral 1 upon x dx. So this is integral cosec v dv is equal to integral 1 upon x dx, and the integral of cosec v is log tan v by 2, and on the right hand side this is log x plus c. Now we need to substitute this v back, so we can see this v is equal to y upon x. So we'll substitute this back. This will be log tan, so in place of v this is y by 2. So this will be y by 2x is equal to log x plus c. So this will be the solution for the homogeneous equation dy by dx is equal to y by x plus x sine y by x. Let's see the third question, which is x square minus y square dx plus 2xy dy is equal to 0. We'll write this in the form of homogeneous differential equation. So we'll keep this here first of all. So this is 2xy dy is equal to, and we'll bring this on the other side, which will be minus of x square minus y square dx. So this will become dy by dx is equal to minus x square minus y square whole upon 2xy. We can solve it further. This is y square minus x square. Just taking this minus inside, this will be minus x square minus minus plus y square. So y square minus x square divided by twice of xy dy by dx. Now we can see this is a homogeneous equation because the degree for this term is 2, degree for this term is also 2, and degree for this term is also 2. So we will perform the substitution. Substitution will be y is equal to vx, and dy by dx will be v plus x dv by dx. So on performing the substitutions, this left hand side will become v plus x dv by dx, and on the right hand side this y square will be substituted by v square x square. This is minus x square whole divided by 2x dot vx. So now we'll solve it. Let's solve v plus x dv upon dx on the left hand side. On the right hand side we can take x square common from the numerator and x square common from the denominator, which will cancel out. So this will become v square minus 1 in the numerator and 2v in the denominator. Now we'll take v on the right hand side. So this is x dv upon dx is equal to v square minus 1 upon 2v minus v. We'll solve it. So this will be v square minus 1, 2v into v. This is minus 2v square upon 2v. So here we can see this v square and minus 2v square will give us minus v square minus 1 upon 2v. So we can see that now we are left with an equation with only two variables x and v, and we can separate the variables and then solve with the variable separable method. So we separate this. So this 2v will come here divided by minus, I am just taking minus sign common, and this will be v square plus 1 with dv, and this is 1 upon x dx. So this is in the variable separable form. We can simply integrate on both the sides. So just applying the sign of integral, we can see this is minus 2v upon v square plus 1 dv is equal to integral 1 upon x dx. This can be solved using the substitution method, where we'll take v square plus 1 as t. So let me write it here. This is v square plus 1 as t. On differentiating this will be 2v dv will be dt. So this in the numerator 2v dv is dt now, and v square plus 1 is t now. So this is minus 1 upon t dt is equal to integral 1 upon x dx. So we can see this 1 upon t is log t, and 1 upon x integral will be log of x. So let me write it here. So this left hand side will be minus of log t, as integral of 1 upon t is log t, and on the right hand side this will be log of x plus c. We need to substitute this t back, so t is v square plus 1. So this will be minus log v square plus 1. This is equal to log x plus c. Now we need to substitute this v back as well. So from here y is equal to vx, we will take v as y upon x. So this will be minus log y square upon x square plus 1 is equal to log x plus c. So we can write that this is the solution of the homogeneous differential equation. So in the next coming lectures, we will be learning about the next method to solve differential equation, which would be linear differential equations. And then in upcoming, we will learning about the exact differential equations.